I started to give you a little taste of balancing simple chemical equations in the last video, but we are really going to dive into it now. Here's some rules. First you need to write the equation using the formulas of the reactants and the products and include the physical states if you know them, but that is the biggest piece. You need to write them correctly. Then we're going to balance the compound with the most elements in the formula first using integers, whole numbers as coefficients. Balance elements on their own last. Check to see that the sum of each element is equal on both sides. And if the coefficients can be simplified, then do so. Let's look at this guy. Calcium carbonate decomposing, this is the decomposition reaction, into calcium oxide and carbon dioxide gas. Here's what I like to do. Like I said in the last video, I like to draw a line underneath of my yield sign because that separates my reactants from my products. And I like to write down my elements on the left. Ca, C, and O. And then I go, how many do I have of each on the left? I have 1 calcium, 1 carbon, 3 oxygens. And on the right I have 1 calcium, 1 oxygen, 1 carbon, and then 2 more oxygens. So 1 plus 2, which is 3 O's total. And then I look piece by piece to see if they match. So my calcium is 1 and 1, my carbon's 1 and 1, my oxygen is 3 and 3. So we're balanced as is. We didn't have to do anything. And this kind of just shows us pictorially that even though I don't have the same compound on both sides, it shows that we have a balanced mass. For example, this sulfur is depicted as this yellow ball. So I have 1 yellow sulfur on the left and 1 yellow sulfur on the right. I have 1, 2, 3, 4 red balls, which would count as my oxygens because there's 3 plus 1 O is 4 O's. And notice I have 4 O's on the right. 1, 2, 3, 4 red spheres. And then 2 H's, which would be the white ones, 1, 2, and 1, 2. And we can see here that this balance is just kind of showing us that I have the same mass on the left as I do on the right. Here's another one that shows methane gas plus ammonia gas to give us HCN and hydrogen gas. And if I were to look at this, I can see that there's 1 carbon on the left, 1 carbon on the right, 1 nitrogen, which I would assume that the blue is nitrogen since this is 1 N and 3 H's, so the whites must be H's. 3 H's plus 1, 2, 3, 4 H's is 7 H's. And notice that I don't have 7 H's on the right. I only have 1, 2, 3. So I need to do some balancing here. I'm going to start this on a clean slate. And let's balance this equation. So I'm going to draw a line here. And since I don't have space below, I'm going to write down my C, H, and N. And I have 1 carbon, 4 H's plus 3 H's is 7 H's, and 1 nitrogen. And on the right I have 1 carbon, 1 nitrogen, and 2 plus 1 is 3 H's. So notice that my carbons are good, my nitrogens are good, but I need more H's on the right. So I got to figure out how to get to 7. Knowing that I have 1 H here, so 1 plus what would give me 7? Well, 1 plus 6 would, right? Okay, well I already have 2 here, so what times 2 would give me 6? That's got to be a 3. Right? Because 3 times 2 here would give me 6 H's plus 1 to give me 7. And now I'm balanced. So we need to never change the subscripts. If I went back here and said, you know what, I need 7 H's on the right. So I'm just going to make this, let's see, we said we needed 6. I'm just going to make that a H6. Nope, we cannot change those subscripts. Can't do it. Illegal. Don't do it. So we got to make sure that our formula is written correctly. Add coefficients before the compound. And then double check. Go top down. Let's look at hydrogen plus oxygen to give us H2O. I have hydrogen and oxygen on both sides. I have 2 H's and 2 O's, 2 H's and 1 O. So we can see here that my H's are good, my O's are not. I need more on the right side. And thinking in multiples, 1 times what would give me 2? So I'm going to go, 1 times 2. Now notice, this says I have 2 H2O's, so that's like saying H2O. There's 1 water, there's a second water. So I now have 4 H's. So I'm going to cross this off. I have 4 H's. I no longer am good. That's okay. It happens. 4 H's and 2 O's. So then I always go back and do top down. Oh, yep, my H's don't match. My left side needs more. And again, I want to think in multiples. If I have 2, how do I get to 4? Well, I need to times my hydrogens by 2. 2 H2s would give me 4 H's. So my H's are good now, my O's are good now. I am balanced. Let's try these. H and Br. I have 2 H's and 2 Brs, 1 H and 1 Br. I like to look at the top first, so I need more H's on the right. So let's make that 2 H's, and that 2 also distributes to the Br. And we have a balanced equation. How about this? Let's make up elements for these. Let's say that these 2 white ones signify H2. And let's say these blue ones signify about N2. And then this makes, if blue is N, it'd be NH3. All right, now let's balance it. H and N, H and N. You could have used any elements you wanted to. 2, 2, 1, and 3. Okay, so I'm going to look at this first and go, oh, well, I need more on the left, but if I'm thinking in multiples, if I were to put a 2 in front of my H2, that'll only give me 4. I can't get to 4 from 3. So, again, think first common multiple that they would have in common. And I would think, if I'm looking at 2 and 3, I would think, oh, 6. How do I get to 6? 2 times 3 would give me 6 H's. 6. So to get to 6 on the right side, I'm going to need a 2 in front of that. That'll give me 2 N's and 6 H's. And now we're balanced. 6 H's, 2 N's on both sides. Let's try this guy. I've got aluminum and bromine. Aluminum and bromine. This is crossed off. Okay, so I have 1 aluminum and 2 bromines, 1 aluminum and 3 bromines. Okay. The aluminums are good. Let's look at the bromines. And again, I want to think the first multiple that they have in common is 6. So let's do the left side first. I need to have a 3 there to give me 6 bromines. I need to have a 2 here to give me 6 bromines, but that also gives me 2 aluminums. So don't forget to go back and give 2 aluminums on the left. And now we're balanced. Let's do this one. Aluminum oxide decomposes into aluminum and O2 gas. Aluminum and oxygen, aluminum and oxygen. 2 aluminums, 3 oxygens, 1 aluminum, 2 oxygens. Okay, so like I said, top down, let's give aluminum more. Give that a 2. I'm going to change color here so we can see it better. A 2 here. All right, that gives me 2 aluminums. And then I'm going to go oxygens needs more. Oh, we're at 3 and 2 again. Okay, let's get to 6. I'll put a 3 here. That gives me 6 oxygens. On the left I need to get to 6. I'm going to put a 2 there. And that gives me 6 oxygens, but oh, it messes up my aluminums. That now gives me 4 aluminums on the left. Let's double check. Oh, my aluminums do not match. So I'm going to go back to the drawing board. I'm going to erase all those. Go back to the drawing board. And I have 1 aluminum currently since I erased that. How do I get to 4? I'm going to need to put a 4 there. So I had to erase my last one because it didn't work. Now we're balanced. All right, let's try writing this last one out. All right, we have elemental iron. So if it's an element and it's iron, we know iron is a solid in its natural state. And chlorine gas, Cl2, chlorine is in Brinkelhoff, so it's diatomic. React to form the salt. Salt is a solid. Iron 3 chloride. And we know that 3 means that iron has a +3 charge, so it must be FeCl3. Let's balance this. I have iron and chlorine. I have 1 iron and 2 chlorines, and here I have 1 iron and 3 chlorines. So let's get to 6. I'm going to put a 2 in front of there to give me 2 irons and 6 chlorines. I need a 2 in front of my Fe, that gives me 2, and I need a 3 in front of Cl2 to give me 6. How do you feel doing this? All right, I'm going to let you do this first one as a review, and I'll give you the answer here in just a minute, but I want to do one with a polyatomic ion. Let's look at this one. I have iron, I have oxygen, I have hydrogen, and then I have SO4. Now, can I break it up into sulfur and then add those oxygens with the other oxygens? Yes. But here's a little trick. If I have a polyatomic ion on the left and the same polyatomic on the right, I can keep it together in a chunk. Watch this. I'm going to keep SO4 together. All right, so on the left I have 2 Fe's, 3 O's, 2 H's, and 1 SO4. On the right I have 2 H's, 1 O, 2 Fe's, and 3 SO4s. All right, so Fe's are good right now. I need triple the oxygens on the right. Not the SO4 oxygens, but where O is. So I'm going to put a 3 in front of where the oxygen is. So that will give me, messes with my H's. It gives me 6 H's and 3 O's. Okay, so the Fe is good, oxygen's good. I need triple the H's on the left. So I'm going to put a 3 in front of that H. That now gives me 6 H's and 3 SO4s. And boom, we're balanced. Let's do this next one. We have aluminum. Now I have a polyatomic. Is there SO4 on the right? Yes, there is. So we can keep it together. Then we have barium. And then we have nitrate. Is nitrate on the right? Yes, so we can keep nitrate together. Two aluminums, 3 sulfates, 1 barium, and 2 nitrates. 1 aluminum, 3 nitrates, 1 barium, 1 SO4. Okay, so at first look, I need double the aluminums on the right. So I'm going to double the aluminum. That gives me 2, and that gives me 6 nitrates. Right? I had 3 nitrates, and I just doubled it. All right, so my aluminums are good. On the right, I need to triple my SO4s because I have 3 on the left. I only have 1 here. So I'm going to triple my SO4s. That gives me 3 bariums and 3 sulfates. Okay, so the aluminums are good, sulfates are good. The left, I have 1 barium, I need 3. So let's triple where my barium is. That gives me 3 bariums, and I just tripled my nitrates. I had 2 times 3 is 6, and now we're balanced. So why don't you pause the video here and do this top one and the bottom one, and we'll check our answers in a minute. Check to see if you got what I got. I have 3 of iron 2 oxides, 2 aluminums, and 3 irons to have a balanced equation. And on the bottom here I would need 2 sodium hydroxides and 2 waters to be balanced. Okay, let's look at this combustion reaction. Don't pay attention to this quite yet. I have C2H6 plus O2 to give me CO2 and H2O. Let's do our list here. CH and O, CH and O. 2, 6, 2. 1, 2, and 2 plus 1 is 3. Okay, let's balance this. I need more carbons on the right, so I'm going to put a 2 here. That gives me 2 carbons, and now 4 O's plus 1 O is 5. I have 6 H's here, so let's put a 3 in front of this H. That'll give me 6 H's. And I have 3 O's plus 4 O's, so that's 7. Now notice my C's are good, my H's are good. Let's look at our O's. How do I get from 2 to 7? Well, that's where this came into play. 3.5 times 2 would give me 7, right? Okay, so that would give me 7, except for, oh wait, you can't have a half. It has to be whole numbers. So we double everything, right? That will make this a whole number. So I'm going to double all of these and make it 2 C2H6 instead of 1. 3.5 times 2 would give me 7. 2 CO2s to 4. 3 waters to 6. Now let's check and see. On the left I have 4 carbons. On the right I have 4 carbons. I have 12 H's and I have 12 H's. And then I have 14 O's. And on the right I have 4 times 2 is 8 plus 6 to have 14 O's. So every once in a while you have to do this. Think combustion reactions. Those are usually the trickiest ones. Why don't you try balancing these two? Pause the video and then come back to check your answers. Did you get the same as me? I hope so. Why don't you practice writing and balancing the following reactions? Pause the video and balance. Check your answers to see how you did. Here's some more practice. If you're feeling like you got this, you feel free to skip ahead and not do the practice. How did you do? Did you get them? Here are some join-in questions for you to try. That wrapped up section 2. Looking at section 3, we're going to look at chemical reactions and recognize that some are reversible and can eventually reach a dynamic equilibrium. Others simply run in one direction until the reactants are used up. These are called irreversible reactions. We're also going to look at the difference between reactant-favored and product-favored reactions at equilibrium. So when writing chemical reactions, we start with our reactants on the left and our products on the right. And so here we have nitrogen gas plus hydrogen gas yields ammonia gas. Some reactions can run in reverse. So notice that ammonia gas can decompose into nitrogen and hydrogen gas. And under these conditions, the reaction can be written with double arrows, which indicates equilibrium, which means the reaction is happening in this direction and it's also happening in this direction. So I can have products and reactants present at all times. Here's a little snippet from our book talking about the reversibility of reactions.
We often think of chemical reactions as completely converting reactants to products, but this is not usually the case. Many reactions lead to incomplete conversion to products. And it's even more important to recognize that all reactions are in principle reversible. For example, ammonia can be synthesized, that is prepared, from nitrogen and hydrogen. But once ammonia is formed, it can decompose to the elements. The reaction is reversible. A great example of reaction reversibility are the stalactites and stalagmites you see in caves. Limestone, calcium carbonate, can dissolve by reacting with CO2 and groundwater to form water-soluble calcium bicarbonate. When the solution flows into an open cave, however, the CO2 can come out of solution, and limestone is redeposited as a stalactite or stalagmite in the cave. Let's go back to the ammonia synthesis, where the balanced equation tells us that 3 moles of hydrogen can react with a mole of nitrogen to produce 2 moles of ammonia. The graph you'll see shows what happens if we begin with a 3-to-1 mixture of hydrogen to nitrogen and follow the reaction as a function of time. The disappearance of hydrogen follows the red curve, and that for nitrogen follows the blue curve. The appearance of ammonia is given by the green curve. Let's look at each aspect of this diagram. When the reaction first begins, nitrogen and hydrogen are consumed rapidly and ammonia forms rapidly. However, the reaction eventually slows down until the concentrations are no longer changing. There's no further macroscopic or readily observable change. After this time, ammonia is still being formed, but some of it is reverting to nitrogen and hydrogen as fast as it is formed. Both the forward and reverse reactions are occurring. We say that the reaction has reached a chemical equilibrium. Let's review some of the most important points. At equilibrium, the reaction vessel contains all 3 compounds in the reaction: nitrogen, hydrogen, and ammonia. Ammonia is being formed and is reverting to the elements at the same time. We refer to this state as a dynamic equilibrium. To signal this state of dynamic equilibrium, we use a double set of arrows between the reactants and the products. The ammonia reaction illustrates an important principle in chemistry, that chemical reactions always proceed spontaneously toward equilibrium. A reaction will never proceed spontaneously in a direction that takes the system away from equilibrium. It is fair now to ask, when a reaction reaches equilibrium, will the reactants be converted completely to products, or will some of the reactants remain? For many of the reactions you will see, the latter is what happens. Regarding this last point, chemists tend to put reactions into 2 broad categories. There are product-favored reactions, that is, reactions in which the reactants are completely or largely converted to products when equilibrium is reached. There are reactant-favored reactions, in which there is a conversion of only a small amount of the reactants to products at equilibrium. Referring to the ammonia reaction diagram above, under those conditions, the formation of ammonia from nitrogen and hydrogen, as pictured, is an example of a reactant-favored reaction, although it is product-favored under other experimental conditions. You will see many other examples of this in your study of chemistry.
Our next section is about aqueous solutions. So we're going to look at the difference between electrolytes and non-electrolytes and look at some examples and predict the solubility of ionic compounds in water. All right, so we have in an aqueous solution, we have water that's acting as a solvent. The solute is what is being dissolved into the solvent. So the solute, in this example here, we have copper 2 chloride is added to water. So the copper 2 chloride is our solute, and the water is our solvent. And we can see that when we add this copper 2 chloride, that the Cu2 plus and the Cl minus ions allow the solid to dissolve. And look what happens here. We know water is electrically positive on one side, right? We have oxygen and we have our hydrogens, and our oxygen's negative 2 charge, right? And our hydrogen's positive 1. So we have a negative end of my water molecule and a positive end of my water molecule. And so what's really cool about how this molecule works is that these charges enable the water to interact with negative and positive ions that's in the aqueous solution. So our copper plus 2, the positive copper is going to be attracted to the negative ends of the water. Notice this is our negative end, the oxygen end of the water. So all of those copper plus 2 ions are surrounded by water molecules, specifically with the oxygen end. And then the chloride ions that are negatively charged, here's our chloride negatively charged, the negative is attracted to the positive end of the water molecule. So all those hydrogens, see how the hydrogens, the water molecule is flipped, and the hydrogen end is attracted to the chloride. Now, when an ionic substance dissolves in water, each ion is surrounded by up to 6 water molecules. So we can see that these ions are now sheathed in water molecules. And then, if we have ionic compounds, we then have a very strong electrolyte. We can put this electrode in there, the bulb is lit, and it shows that this solution conducts electricity well. And a strong electrolyte is one that is completely 100% the solute dissociates into the ions. So the CuCl2 dissociates into copper plus 2 and Cl minus ions. Now, a non-electrolyte, we can see that the bulb is not lit up, so it's not conducting. And an example here is ethanol. Ethanol is a molecular compound, and it's not going to conduct electricity because there's no ions present. Now, a weak electrolyte, we can see that this bulb is dimly lit, so it's conducting very poorly. And I'm going to show you on the next slide how acetic acid is an example of this. And at only 0.5% of acetic acid will dissociate into acetate and H+. Because remember, acetic acid is HC2H3O2. And again, splitting into the H+ and the acetate minus ions is very little. So that's a weak electrolyte. There's very few ions present in solution. So again, if it is an electrolyte and it conducts electricity, that means that it is disassociated 100% into the ions. For example, here's 3 examples. Sodium chloride, we can see that we started as a solid, and when we put that solute into our solvent water, that Na became Na plus ions, again an aqueous solution, Cl minus ions. Barium nitrate as a solid, and then we dissolved it in water, so we have our barium plus 2 ions and nitrate ions. Barium chloride, again, Ba plus 2 ions and chloride ions. Now, some molecular compounds, like strong acids, and weak bases, such as hydrochloric acid, are good electrolytes. And there are weak electrolytes, like we said, the acetic acid. However, only 0.5% of the molecules of acetic acid ionize into acetate and hydronium ions. Now then we have the non-electrolytes, like we said, the ethanol, sucrose, antifreeze, which is ethylene glycol. That's when we have molecules present, not ions. And here's just a little cheat sheet chart to kind of show you, again, Looking at my solute, if it's an ionic compound, yes, it's going to be a strong electrolyte because it's splitting into the ions. Same with if we look at acids and bases. Strong acids are definitely strong electrolytes. Now, weak acids and weak bases, they're going to be weak electrolytes. And then molecular compounds are always going to be our non-electrolyte, the molecules.